So picture a book cover in your mind for a second. Right in the center, there is our planet, Earth, but it's entirely enclosed inside this round glass laboratory flask.
Right, like a chemistry setup.
Exactly. And sticking out of the central flask is this bizarre network of glass tubes, and they're connecting our world to other bubbling lab flasks.
Yeah, and the contents of those other flasks are pretty wild. I mean, one holds a red car.
Right. Another holds a herd of cows. Another has burning coal. There's even a crossed-out spray can of CFCs, and it's like shining this harsh light onto the globe.
It's a striking image, and it perfectly captures the premise we are exploring today, drawn from William W. Hayes' book, Experimenting on a Small Planet. The visual tells you immediately that humanity isn't just, living on Earth. We are actively tinkering with it.
Yeah, the central thesis here is that humanity is currently, and largely unwittingly, conducting this grand, uncontrolled experiment on our own home. And the mission of our deep dive today is to explore the twisting, incredibly surprising path of how we actually figured this out.
Because it wasn't a straight line, right?
Not at all. We are going to look at how seemingly entirely disconnected fields, physics, chemistry, biology, deep-time geology, how they all kind of violently collided to help us understand the mechanics of this massive planetary experiment. Okay, let's unpack this.
Let's do it.
When I look at that lab flask metaphor, my mind immediately goes to those science fiction movies, where humanity travels to Mars or some barren rock and uses massive machines to terraform it.
Right, to make it breathable and Earth-like.
Exactly. But looking at these sources, it feels like we are currently anthropoforming our own planet, just without a safety manual.
We are absolutely anthropoforming Earth. We're changing its fundamental operating system to reflect our industrial footprint. But to truly understand the scale of this experiment and, the danger of missing that safety manual, we really need to look back at when the scientific community first realized the test was already well underway.
And the setting for that realization is wild. It takes us right to the height of the Cold War. Leningrad, 1982.
Yeah, it's a fascinating moment.
This scene from the book is incredibly cinematic. It's July 4th. William Hay, the author, who is a geologist, is sitting in the famous pre-revolutionary Astoria Hotel in Leningrad.
Right.
And the sun is barely dipping below the horizon. It's those famous Russian white nights where it never gets truly dark. And he is having dinner with Mikhail Budiko, a tremendously distinguished Soviet climate scientist.
And Budiko wasn't just, a purely academic figure tucked away in some lab.
No, he was a big deal.
A very big deal. He had massive influence over Soviet state policy, which at the time was really driven by this philosophy of completely dominating nature. But he had recently convinced the Soviet leadership to abandon a truly colossal engineering project.
Oh, right, the river dams.
Yes. Soviet engineers had drawn up this grand plan to dam the major Siberian rivers, the ones that flow north into the Arctic Ocean, and divert all that fresh water south for agriculture.
Which, on paper, sounds like a massive win for Soviet farming, right?
Yeah.
To turn a frozen wasteland into the breadbasket of the world.
It sounds great until you look at the thermodynamics. Budiko pointed out a catastrophic side effect. He realized that cutting off that specific flow of relatively warm, fresh water would fundamentally alter the Arctic Ocean.
It would stop the ice from forming.
Exactly. It would prevent the formation of sea ice. And he argued that losing that ice cover would completely wreck the climate of the Northern Hemisphere and, ironically, destroy the very Soviet food supply they were trying to increase. So he single-handedly stopped one of the largest river diversions in human history.
Wow. Okay, so they're sitting at this dinner, the vodka's flowing, the midnight sun is shining, and Hay asks Budiko a hypothetical question about the future.
Right.
He asks, considering the rising CO2 emissions from burning fossil fuels, is it possible the Arctic sea ice might melt anyway?
And Budiko's reaction is chilling.
Literally grabs Hay's sleeve. He looks him dead in the eye and delivers this warning. He says, Professor Hay, it is going to happen no matter what we do now. Budiko tells him that stopping the river dams only avoided sudden climate change. But the CO2 already pumping into the atmosphere guarantees the Arctic ice will eventually melt. The best we can hope for, he says, is to keep the changes in bounds so it doesn't become a complete disaster.
And that really illustrates a crucial shift in terminology that the text highlights. We often hear the term global warming, which implies this gentle, gradual, almost pleasant rise in temperature.
Right, like turning up a thermostat in a chilly room.
Exactly. But the reality, as climatologist Herman Flown predicted and Tom Friedman later popularized, is much closer to global weirding.
global weirding. It's a terrifyingly accurate way to describe it.
Because the warming isn't uniform. As the planet's energy balance shifts and that Arctic ice vanishes, the entire climate system becomes unstable. What you actually experience are chaotic extremes.
Like the highest highs, the lowest lows.
Right. Unprecedented droughts followed immediately by catastrophic floods. It is a complete destabilization of the weather patterns that human agriculture relies on.
But wait, let me play devil's advocate for a second here. Because humans have been cutting down forests and altering landscapes for centuries.
Oh, absolutely.
The text even points out that early American colonists, including Thomas Jefferson, actively wanted to change the climate. They thought the harsh, humid, disease-ridden North American weather was terrible.
Right, they hated it.
And they honestly believed that if they just chopped down enough forests, they could warm the continent up and make it more civilized, like Europe. So how is what we're doing today any different than the local land management we've always done? At what point did the scientific community realize this wasn't just, chopping down trees in the backyard, but a global chain reaction?
Well, to realize the climate was changing abnormally on a planetary scale, scientists first had to figure out what normal looked like.
Okay, that makes sense.
You can't detect a global anomaly if you don't have a baseline. And finding that baseline required a monumental conceptual leap. It required the discovery of deep geologic time.
Staring into the abyss.
Yes.
There's this fantastic cartoon in the book by Greg Ray. It shows two figures, John Playfair and James Hutton, in 1788. And they're standing at a jagged rock formation in Scotland called Sycamore Point.
It's a great illustration.
Hutton is literally peering through a crack in the rocks into this glowing, dark void, the abyss of time.
That cartoon captures a profound turning point in human thought. Because before Sycamore Point, the accepted age of the Earth, based on historical and religious texts, was measured in mere thousands of years.
Right, a very young Earth.
But looking at the layers of rock, they're these horizontal layers of red sandstone resting directly on top of vertical layers of graywack. Hutton realized that the immense cycles of erosion, deposition, and tectonic uplift required an almost unfathomable amount of time.
Like millions, perhaps billions of years.
Exactly. And once geologists started charting that massive abyss, they uncovered the Earth's long-term climate history. And it turns out our planet basically has two primary moods.
Only two.
Yeah. What's fascinating here is that the Earth does not like to be in the middle. It strongly prefers one of two dominant states. The first is the greenhouse state.
Okay.
For about 75% of Earth's history, the planet has been in this state. It is incredibly warm, sea levels are high, and there is absolutely no permanent ice at the poles.
So if you were standing on a greenhouse Earth, you'd be sweating at the North Pole.
Basically, yeah.
What?
Dinosaurs roamed a greenhouse world.
Wow. And then there's the other 25% of the time.
Right, the icehouse state. This is a much colder planet, characterized by the presence of large, permanent ice sheets at the poles. And the revelation that truly shifts your perspective is this. We are currently living in an icehouse state.
We're in the 25%.
Yes, it began about 35 million years ago. But within this icehouse, we are in a very rare, brief, and unusually warm interglacial period.
Which is driven by those Milankovitch cycles, right? The natural wobbles in the Earth's orbit that slightly change how much sunlight we get.
Exactly. Those orbital wobbles act as a natural pacemaker. They dictate the rhythm of ice ages expanding and retreating over tens of thousands of years. They are the reason we are currently in this brief, warm interglacial window.
Let's put the sheer scale of that window in perspective for everyone listening, because this blew my mind. If you take the entire history of the Earth and compress it into a single 24-hour clock,
Okay.
all of human civilization, I mean, everything from the first farming villages to the smartphone in your pocket, has happened in the last 1/10 of a second.
It's staggering.
We built our entire global society during a tiny, unusually stable, relatively warm blip inside a long-term deep freeze. So if our entire existence is just a fraction of a second in an icehouse world, and we are now pumping carbon into the sky, how easily can this grand experiment accidentally flip us all the way back into greenhouse world?
To answer that, we have to look under the hood of the climate system itself. We have to understand the mechanical levers and gears that actually control that switch between icehouse and greenhouse. And the first, perhaps most powerful lever, is something called albedo.
Basically how shiny or reflective the Earth is.
Exactly.
The book uses another great illustration for this. It has little Cupid-like angels sitting on a chunk of white ice, holding up mirrors to bounce the sun's radiation right back out into dark space.
It's a perfect visual. White surfaces like ice and snow have a high albedo. They reflect incoming solar energy away, keeping the planet cool. Dark surfaces like the open ocean have a low albedo. They absorb the sun's energy, warming the planet up.
It's a constant tug-of-war.
It is. But albedo doesn't act alone. It is controlled by the atmosphere, specifically greenhouse gases.
And the book makes a really crucial distinction here between the two major greenhouse gases. You've got HOH, which is water vapor, and CO2, carbon dioxide. I think a lot of people don't realize water vapor is even a factor.
Oh, water vapor is actually the most abundant greenhouse gas on Earth by far, and it traps a massive amount of heat. But water vapor has a built-in weakness.
What's that?
It requires heat to stay in the atmosphere. As air cools, water vapor condenses and falls out as rain or snow.
Oh, right. Which leads to the massive aha moment from NCR scientist Warren Washington.
Oh, yes.
He was trying to figure out why simply adding a little CO2 to the air disproportionately warms the poles. Because at the equator, it's hot, so the air is constantly full of water vapor acting as a heavy, wet greenhouse blanket.
Right.
But at the North and South poles, the air is absolutely freezing. It is far too cold to hold any significant water vapor.
The poles are essentially dry deserts when it comes to water vapor. So in those freezing, highly reflective regions, carbon dioxide becomes the ultimate thermostat.
Because it doesn't freeze out, right?
Exactly. CO2 doesn't freeze out of the air at those temperatures. I mean, it takes minus 109 degrees Fahrenheit to freeze CO2. So it remains in the atmosphere to trap heat.
Here's where it gets really interesting. If CO2 levels rise even slightly, it traps just enough heat at the poles to warm things up. That extra heat melts a little bit of the highly reflective white ice, exposing the dark, heat-absorbing ocean water underneath.
And then the tug-of-war shifts.
Right. That dark water absorbs more sun, which melts more ice, which exposes more dark water. It is a massive, runaway, positive feedback loop.
And positive feedback loops in nature lead to rapid, violent changes. They destabilize systems. To truly grasp how unstable our Earth's setup is, the author asks you to imagine a brilliant thought experiment.
The hypothetical Holstein planet.
Yes.
Imagine you are standing on a planet named after the black and white cow. But on this world, the physical laws are completely inverted. The snow and ice are pitch black, and the look of water is brilliant white.
Think about the mechanics of standing on that Holstein world. If the black snow absorbs heat from the sun, it melts into white water.
Right.
That white water then reflects the sun's heat away, which cools the planet down, causing the white water to freeze right back into black snow.
It's a perfect negative feedback loop. Any change instantly triggers a reaction that cancels it out. A planet like that would be incredibly stable, locked forever exactly at the freezing point of water.
But Earth is the exact opposite of the Holstein planet. Our white ice and dark water create a highly volatile positive feedback loop. Once the ice starts to melt and expose dark water, the system actively accelerates its own warming. It is a deeply precarious balance.
So if I'm tracking this, we know that CO2 is the thermostat at the poles, and we know it controls the runaway train of albedo. But the real shocker for me in Hayes' book is how humanity actually discovered the inner workings of this massive global system.
Oh, the path to discovery is incredible.
Because we didn't figure it out just by looking at the sky or charting ice. We figured it out by looking through microscopes and falling completely down the quantum physics rabbit hole.
Let's start with the microscope. You simply cannot understand Earth's climate without understanding a microscopic single-celled ocean algae called Emiliania huxleyi.
The tachosphere. This thing is tiny. It's about 2 microns across, which is roughly a couple of thousandths of an inch. But looking at it under an electron microscope, it is gorgeous.
It really is.
The single cell is wrapped in this protective armor made of complex overlapping plates of calcium carbonate, which are called coccoliths.
They look like tiny, intricate, chalky hubcaps. And while they are individually invisible to the naked eye, they bloom in the oceans in such staggering numbers that you can literally see the color of the water change from space.
Oh, wow.
But their true importance lies in what happens when they die.
Right. Their tiny calcium carbonate shells drift down to the bottom of the ocean, building up massive layers of sediment over millions of years. And because calcium carbonate is literally made of carbon, these microscopic creatures are actually one of the major participants in Earth's entire carbon cycle.
They're essential.
They are grabbing the thermostat knob carbon out of the surface environment and burying it in the deep.
If we connect this to the bigger picture, the biology tells us where the carbon goes and how the Earth naturally regulates it over deep time. But to understand how that carbon, in the form of CO2 gas, actually traps heat in the atmosphere, we have to look at physics.
Okay, so from biology to physics.
Right. And in the late 19th century, classical physics hit a massive brick wall.
Because classical physics was chugging along perfectly, explaining gravity, planetary orbits, and steam engines. But it completely failed to explain something called black body radiation and the ultraviolet
It
catastrophe.
was a huge problem.
So to figure out why the sky is warming, we had to invent an entirely new branch of physics. That feels like having to understand the subatomic structure of aluminum just to figure out why my car's radiator is broken.
It does seem extreme, but it was necessary.
How did we get from A to B? Why did classical physics fail so spectacularly at explaining the greenhouse effect?
Classical physics failed because it viewed energy like light and heat as a continuous, unbroken wave.
Like a smooth slope.
Exactly. And under that classical wave theory, a glowing object, or a vibrating gas molecule, should emit an infinite amount of high-frequency ultraviolet energy.
But that's not what happens in reality.
Yeah.
Hence the catastrophe. The math literally said we should all be fried by ultraviolet light coming off of everything in the room, which clearly wasn't happening.
Right. So to solve this impossible contradiction, scientists like Max Planck had to make a radical proposition. They had to suggest that energy isn't a continuous smooth wave. Rather, it comes in discrete, indivisible little packets, or quanta.
The book has an illustration of Alice and the White Rabbit tumbling down the hole, surrounded by all these bizarre, glowing quantum monster shapes. It really was like stepping into a new universe.
It absolutely was. Think of classical physics like walking up a smooth ramp. You can stand at any elevation on that ramp.
Right.
Quantum mechanics is like climbing a ladder. You can only stand on the specific, discrete rungs. You cannot stand in the empty space between them.
Okay, that makes sense.
And once you understand that energy is quantized, that it has rungs, you suddenly realize that gas molecules, like CO2, can only absorb and emit very specific packets of energy.
Ah, so the rungs of a CO2 molecule perfectly match the energy packets of infrared heat radiating off the Earth. It catches that heat.
Yes.
But the visible light coming from the sun has a different energy size.
Mm.
It doesn't match the rungs, so the CO2 just lets it pass right through.
You've got it. Without quantum mechanics, we would have absolutely no mathematical or physical framework to prove that a few parts per million of an invisible gas can act as a one-way thermal blanket, fundamentally altering the energy balance of an entire planet.
It is just staggering. I mean, we needed to understand the bizarre rules of the subatomic quantum realm just to explain how the sky traps heat.
Yeah.
And we needed to understand the biology of a 2-micron ocean algae to understand where that thermal blanket comes from.
It's all connected.
It takes a specific kind of mind to connect microscopic ocean algae to the quantum mechanics of a warming sky. And that brings us to the unique way William Hay tells this story. This deep dive has spanned from vodka-soaked Soviet dinner parties to deep geologic time to the birth of quantum mechanics. Interspersed through all this heavy science, Hay includes these sections he calls intermezzi.
Right, the autobiographical interludes, they serve a very specific purpose in the text.
They are essentially his personal memoirs slipped into a textbook to, as he says, relieve the tedium of learning. He talks about being an undergrad in Munich in the 1950s, drinking beer and debating philosophy in local Neiben.
It sounds like a fun time.
Right. And he talks about scuba diving in the Gulf Stream, staring down into the black abyss to hunt for those tiny, beautiful foraminifera. It's a constant reminder to you, the reader, that science isn't just dry data spit out by a computer.
Not at all.
It is a profoundly human adventure, driven by immense curiosity, weird dinner parties, and quite frankly, serendipity.
And this raises an important question. When we look at all these incredibly diverse fields, what is the ultimate conclusion we must draw?
Right, what's the bottom line?
The synthesis of all this knowledge, from the abyss of geologic time showing us the volatility of icehouse and greenhouse states, to the quantum mechanics explaining the CO2 thermostat, to the biological drivers of the carbon cycle, it all points to one undeniable reality. Humanity is actively running a grand, uncontrolled experiment on our only home.
Yeah.
We are pushing the very levers that have historically caused massive, violent shifts in the Earth's operating system.
So what does this all mean? Well, I want to leave you with one final, totally mind-bending thought from the author. It's something Hay actually joked about at a geology conference way back in 1975.
Okay, what is it?
Think back to those beautiful, microscopic, calcareous nanoplankton building their tiny chalky shields of carbon and falling to the ocean floor.
Caucospheres, right.
Exactly. If they continue to take carbon from the surface and drop it to the bottom of the sea eventually, shifting tectonic plates will subduct that ocean floor, dragging all that buried carbon deep down into the Earth's fiery mantle.
Oh, wow. Over a vast enough timescale, they are essentially a biological doomsday machine.
Yes. Given enough hundreds of millions of years, these invisible little life forms will literally strip all the life-giving carbon from the Earth's surface and crush it deep inside the mantle, turning the building blocks of life into buried diamonds.
That's incredible.
It's an incredible reminder of how interconnected every single layer of this planet truly is. So the next time you look up at the sky or hear a debate about the climate, remember the image we started with. Our Earth inside a fragile glass laboratory flask. We are running the experiment right now, playing with the thermostat of a world suspended precariously between an ice house and a greenhouse, driven by quantum rules and microscopic life, and we are doing it all without a safety manual.